So let M denote a smooth manifold smooth means differentiable of class C to infinity. Often we will assume that we can differentiate functions infinitely many times. This is useful to make several arguments work without obstructions. And a smooth function is a C infinity function. So an infinitely differentiable function. Let P be a point of M a smooth function in a neighborhood U of P is the pair Fu where f is a function with real values, is a C infinity function. On U. So we denote it like this. So this is a smooth function. We can define an equivalence relation for smooth functions. We say that two smooth functions are equivalent. And we write f equivalent to g if there exists a neighborhood of P a neighborhood W of the point P where they coincide. So such that f restricted to W coincides with G restricted to W. So each smooth function is a pair, so it's associated with a neighborhood of P different from W, but if there is a neighborhood of W of P where they coincide, then they may be different outside of W, but if they coincide in a neighborhood, then they are equivalent. Okay, so everything is referred to a point P. In this equivalence relation, everything is referred to a point P of the manifold M. And then you can take the quotient GP between the set of smooth functions in P and the equivalence relation. And that quotient is called space of the germs of the smooth functions in P. And that is denoted by G of P. So that's a space of smooth functions with an equivalence relation, basically, that tells you that two functions have to be identified if they coincide in a neighborhood, in any, no matter how small it can be, any neighborhood of P. So basically, it's like saying that they coincide with in P with all their derivatives. A derivation in P is a map X from the space of germs of functions, so smooth functions in P, to the real line. Unfortunately, the symbol X will be used for many different things. We used it for the topological space, now we're using it for the derivation. Soon we will use it for vector fields. Even in the notes that I suggested yesterday, you will find it used in different contexts, so I hope this will not generate confusion, but it can have different meanings. So in this case, it's a derivation. A derivation is a map of this from these spaces such that X of a sum is the sum. So X of F plus G is X of F plus X of G. This is the first assumption. Linearity, if you want. Then X of a constant is 0, where lambda is a real constant. And then, as you can imagine, since these are called derivations, you have Leibniz rule, because functions can be multiplied. So X of F plus G is F times X of G plus X of F times G. And everything is required to hold in P. So this is a derivation in P. In particular, these assumptions imply that X of lambda times a function F, we didn't add this as a separate assumption because it is a consequence of those. If you apply the Leibniz rule, so the third assumption, this one, you will get lambda x of f plus fx of lambda. But if you apply the first assumption, x of lambda is 0. And so you can take the constant out of the derivation. Okay, this is the called derivation, and the space of derivations in P is denoted by d of P, and it is a vector space. Because a linear combination of derivations that satisfy those properties satisfies those properties, and therefore it is a derivation. Now we want to study this space a little bit better, and we want to work out a basis for this space, see which objects generate this space. So to do that, we first state and prove a simple property of C infinity functions. So this is an aside note. Let U denote an open set of Rn P a point of U, and F an infinitely differentiable function of defined on U, a smooth function on U. Then there exist functions, smooth functions, GI, such that for every x in U, we have the following identity: f of x minus f of p, f calculated in the coordinates of p, can be written this way, which is more or less like an improved Taylor expansion. So the sum on I of xi minus xi, the coordinates calculated in P, times these functions gi of x. So they are not like the first derivatives, they are functions. They are not the first derivatives calculated in P, but they are more or less related. Indeed, the second property is that these functions gi calculated in P coincide with the derivatives, the partial derivatives of the functions xi calculated in P. So it's very simple to prove that such C infinity functions exist, and here is the proof. Sufficient to write them explicitly. Let us assume, for simplicity, that the point P has coordinates equal to 0, so that's the origin. and then you can write this formula. F of x minus f of 0 is equal to the integral from 0 to 1 in dt of the total derivative df over dt, calculated where? In tx1 txn. So this is an obvious identity because it's the integral of a total derivative, so the result of the integral is the value of the function f in for t equal 1, where you have f of x, minus the value of f for t equals 0, where you have f of 0. So this is obviously true. And to convert it in the form that we want, you just calculate that total derivative by means of partial derivatives, because the derivative with respect to t is equal to the partial derivative of x with respect to xi, calculated in tx times xi. So this can be written as xi gi of x, and gi of x is this object here, the integral of the partial derivative. So gi of x is the integral from 0 to 1 in dt of the partial derivative of f with respect to xi, calculated in tx. And the other property we want to show is that gi calculated in 0, p is 0, is the partial derivative of f calculated in 0. So gi of 0 is equal, if you put x equal to 0, the integral is the integral of a constant, and it is equal to 1 times the constant, which is exactly this thing. So this identity is useful. Such functions exist. They are C-infinity functions. These functions are C-infinity because f is infinitely differentiable, and an integral can only improve the differentiability. So you have the integral of a derivative, you don't lose any differentiability property. Now we want to show, to write a basis for the derivations. So again, let U denote an open set of Rn. So we work with an open set of Rn because, as we said yesterday, when we want to describe a manifold, we can describe it as a collection of open sets that cover the manifold, and then when we move in the intersection, we have rules to make a change of coordinates and then continue on another chart. So it's useful to first focus on a single open set of Rn, because then every portion of our manifold will be diffeomorphic to that. So let U denote an open set of Rn and P the point of U. Then we want to show that these objects, xi, which are the partial derivatives with respect to xi, the coordinates of that open set of Rn, calculated in P, is a basis for the derivation of the space dp of derivations in P. So what are these objects? Again, let's recall that the derivation is an application that acts on germs of functions. So we have to explain how these act on functions. So if f is a function from u to r, it's an infinity function, then xi of f denotes simply the partial derivative of x with respect to xi calculated in P. So that's a linear map from a C infinity function on u, which is f, to the real line, because on the right hand side you have a real number, which is the value of the partial derivative calculated in P. In particular, let us take a very simple C infinity function, f equal to a coordinate, xj, then xi, capital Xi, acting on small xj is, of course, delta ij. So we want to prove that these xi's are a basis of the space of derivations, and for that to be true, we have to show that they generate the entire space. They generate dp. So let x be a derivation, any element of dp. And let us define x, capital X on xi equal to ai. So we take that derivation and we apply it to the functions xi, which are simple C infinity functions. They give real numbers. We call them ai. Then we want to show that x is this linear combination of the xi's, so which proves that the xi's generate the entire space of derivations. And to prove that, we consider the difference and prove that it is zero. The difference y, which is x minus this is still a derivation, and we want to show that this derivation is identically zero. We want to show y of f equal to 0 for every f belonging to the space of germs of smooth functions in P. And that's where the theorem we proved earlier, which was this one, for writing conveniently the function f, will become useful. So first we compute y on, again, the simple functions xi. So that is capital X on xi minus, let's call the repeated indices. The repeated indices are summed, and the summation is understood, so we can change the names of those. Well, by definition, capital X on xi is ai, and we have shown previously that capital Xi on small xj is the delta tensor, so you have 0 in this case. And that's fine. And now we want to compute y of f. And to do that, we use the theorem we proved earlier, that f of x is f of p. We move f of p to the right-hand side, so f of p plus that sum. F of x is equal to f of p plus sum xi minus xi of p gi of x. And then the result is simple, because you can say that y of f, y is linear, it's a derivation. So it's y of fp, but y of fp is 0 because this is a constant. Then you have a sum, so the y acting on a sum is the sum of y acting on the elements you are summing. And then these elements are products, so you can use the Leibniz rule for each, and you will have y of xi minus xip times gi of x plus xi minus xip times y of gi of x. I write it on the other page. Plus sum of xi minus xi of p times y on acting on gi of x. So it's important to know that gi of x are C infinity functions, because that allows us to do that. Okay, so y of fp is 0 because it's a constant. Y of xi minus xip is 0 because y of xi is 0. And y of xip is again 0 because that's a constant. So again, this is 0. And we remain with the other thing. But it's obvious that this object vanishes in P. I repeat that everything we are talking about here has to do with the point P. And we want to show that this is a basis of the derivations, of the space of derivations in P. And so we just showed precisely that. So we can identify the derivations in P with these xi's, which are partial derivatives. Here they are. Now, the tangent space in P is isomorphic to the space of derivations in P. They are basically the same space. So this is another way to describe the tangent space, and it will be closer to what we will need later. So the tangent space TP what happens here? Let me get out and save. There's some problem here. So the tangent space TP in P is isomorphic to the space dP of derivations in P. Isomorphic means there are two vector spaces, and in a vector space you can have you can sum vectors and multiply them by scalars, and so their isomorphism must preserve the linearity property. So the sum must be sent into a sum, and the multiplication of by a scalar must be sent into a multiplication of a scalar by a scalar. These are quite simple properties, so it's just sufficient to write down explicitly the map, this isomorphism, to convince ourselves that indeed the two spaces are isomorphic. So the map will be called zeta. We recall that the space of the tangent space is an equivalent space of curves in P, which are equivalent when they have the same tangent vector in P. So let V be an element of TP, which means that V is an equivalent class of curves that, let's say that gamma of 0 is P. So for t equals 0, they all go, they cross P, and they have to cross P with the same tangent vector. All representatives of the equivalence class V. Then the isomorphism is as follows. Zeta of V, so the isomorphism must send a curve, an equivalent class of curves, an element of TP, into a derivation. So we have to, the zeta of V must be a derivation. So a derivation must act on germs of functions, let's say on functions f, a representative of another equivalent class, and it is this. The derivative with respect to t of f calculated on gamma of t, where gamma of t is any representative of the equivalence class of V, and that calculated in P, which means t equals 0. So that is a derivation indeed, and now we make this map more explicit, but it will be clear that this is an isomorphism. Let's consider very simple curves. If we want a basis of curves, the curves that are equivalent to moving along the ith axis. So AI are a basis of versors, each one pointing along a certain the ith direction, that is EI, and by VI we mean the equivalence class of curves which has this very simple representative which amounts to moving along the x direction, then the y direction, then the z direction, and so on and so forth. Let's apply this definition to this particular representative here. So you will have zeta of vi, which acts on a certain germ function f, that is equal to the derivative with respect to t of the function f calculated along that curve, which means that it is calculated for all coordinates equal to 0 except for the ith coordinate, which is equal to t, and then 0, and then you have to compute that at t equals 0. So obviously this is nothing but the derivative with respect to xi calculated in t equals 0, which means xi of f in p. And so you can say that the isomorphism is the one that sends, you can drop f on both sides, and that is the isomorphism. Okay, so yes, xi, these elements are the basis of the derivations. Now we can define a vector field. What is a vector field? Is a linear function v, this time we call it v, because actually x, it's called x, unfortunately. Linear function x from the space of k times differentiable functions defined on the manifold f, M, to the space of k minus 1 times differentiable functions defined on a manifold M. So k will be equal to infinity most of the time, so this simply means a linear function that associates a smooth function with another smooth function, such that it's like a derivative, a derivation, because you see that the degree of differentiability is lowered by 1 unit. So such that the only assumption has to obey, besides being linear, is like a derivation, the Leibniz rule. So x of fg is f times x of g plus g times x of f. What's the difference between a vector field and what we have said so far? That a vector field is the same object we talked about so far, but defined on the entire manifold. That's an object that's defined on the manifold, not just on a point P, not just on a neighborhood of P, and not just on an open set. Everything we said so far can be easily extended to an open set. And now we want to extend it to the entire manifold, which means that in every open set we can do what we have just did, but we have to specify what happens in the intersection between two open sets of the cover that defines the manifold. And for that to work, we just need to explain how to transform how this object, well, first we have to see how to write this object in coordinates, which will be very similar to what we have just done, and then how to transform it from one set of coordinates to another one, so from one chart to another. So locally, which means in a specific open set, in a specific chart, locally, this is a derivation. And instead of being on a single point, it's on the entire open set. So locally, we can have the basis d over dxi without restricting it to the point P, because it's on all points of an open set. And any x will be a linear combination of those. So the coefficient will depend on the point P. So that's how a vector field, what the vector field looks like in a single open set. In the intersection between two charts, so recall that a chart is a pair open set coordinates, but sometimes you can have two charts which have the same open set, just two different coordinates for the same open set. Those are two different charts. So you can just change coordinates without changing the open set. And the intersection in that case is the entire open set. So the same open set with two different coordinate systems is two different charts. So let us call x and y the two coordinate systems. And in the intersection, you can really play with coordinates and derivatives as you are accustomed to, because we are in Rn. So we will have two representations for the same vector field, one in coordinates y with coefficients that we call b, I, y, and the other one in coordinates x with coefficients a, I, x. And it is obvious that you can, when you make the change of coordinates, that is to say, you write y as a function of x, you can use the Leibniz rule, and d over dyi can be written as d over dx j dxj over dyi, which means that you have the following transformation rule. And actually we have to change the names of the various indices. So this must become I, this I, and this must become j and j. So we have j, j, and I. Okay, this is the transformation rule, or you can write b I y of x equals a j of x d over d. So now y is above and x is below. So when you give such objects in every open set and they transform with the correct rules in the intersections, then what you are giving is a vector field, which is defined on the entire manifold. Chi infinity M denotes the space of vector fields, the space of smooth vector fields, which means infinity vector fields, of a smooth manifold. So everything is smooth here. That means what? It means that all the functions, all the coordinate changes have to be infinitely differentiable. All the functions A are infinitely differentiable, so in every coordinate system your vector field is described by infinitely differentiable functions. This is then 4, so we can stop here.